Hey, Science Nines. Today we're going to be talking about topics 3.1 and 3.2 in the electricity unit, all about energy transformation. So, before we get started on energy transformations, maybe we should quickly discuss what energy is. It's a term that's used a lot. You may not actually know what the actual definition of energy is, but strictly speaking, energy is the ability of something to do work. And there's all sorts of forms of energy, as you've been discovering. We've talked about electrical energy throughout this entire unit, how we can use chemical energy to basically to make that electrical energy through batteries and cells. But when in this unit, we're discussing essentially four forms of energy. We're discussing chemical energy, electrical energy, mechanical energy, and thermal energy. So chemical energy is the energy produced by chemical reactions. Electrical energy is produced by the flow of electrons through an electrical circuit. Mechanical energy is the energy of movement, something moving to generate energy, and thermal energy is the energy created through an object releasing heat. So those are the four forms of energy that we're sort of mainly discussing as part of this unit. Um, they can be converted from one form to another. So energy is constantly being converted. We've seen that already earlier in the unit. We discussed again cells and batteries. They're using chemical reactions to essentially release electrons, which will then create electrical energy. That electrical energy then would hit a load in a circuit like a light bulb, and that electrical energy would then get converted into thermal energy or even light energy to basically make that light bulb light up and, of course, heat up when it lights up as well. So this is nothing that's a new concept. You've been seeing this throughout this unit, and even back to units B and C when we discuss chemistry as well. Um, and just so you know, energy, the units for energy, and I didn't write that on the board. I'm going to write it down right now. Whenever we deal with energy, the units for energy are called joules. So joules are your units of energy, and that'll be the units that we use for that particular measurement in physics. Again, when we have a transfer of energy from one form to another, if I'm starting with, let's say, in a battery, chemical energy that then gets converted to electrical energy, the chemical energy would be my input energy, my electrical energy would be the output energy. If that electrical energy then hits a light bulb in the circuit, a load in the circuit, then the electrical energy is now the input energy, and then the light or the heat energy produced by the light bulb because of the resistance in the load, that would then be the output energy. So that's just something to keep in mind. Is there an example of another example of such a transformation? Yeah, one that's in your textbook that's specifically listed in your textbook in 3.1 is something called a thermocouple. A thermocouple is a device that basically converts heat energy into electrical energy or thermal energy into electrical energy. And there's some information about how it actually works right down here on that slide. If you're interested, a cute little video here to watch, a music video that was produced a few years ago, and that video is all about energy transformations. Take a watch. It's nothing officially educational, but it is a pretty cool video to watch, showing all the different forms of energy transfer that are occurring in that music video. So give that one a watch if you're interested or need a bit of a break, even though I just started our conversation today. That was 3.1. That was literally one whole topic of the textbook that quickly. Now we're going to get into the meat and the potatoes about energy transformations. Today we're going to be discussing, the majority of today's discussion is going to be electrical to mechanical. How do we take electrical energy and convert it into mechanical energy? Like, you're driving your vehicle, you're using electrical power to basically create a vehicle that moves. So how do we do that? There is a little bit of history here, and I want to discuss a couple of scientists before I discuss the actual the creation of energy, using mechanical energy, using electrical energy. The first scientist I want to discuss is a guy by the name of Oersted, Hans Christian Oersted, who was a Danish scientist, and he was doing some experiments in the early 1800s and discovered that when he had a wire with a current running through it, so they were doing experiments on early electrical experiments. This would have been around the time of Volta, Ohm, all these early scientists that were doing these experiments. He was doing experiments, and when he found that if he had an electrical wire that was running an electrical current through it, and he would actually put a compass beside it. The compass would move. The compass needle would move off of north. And what this showed him was that an electrical current is actually producing a magnetic field. So he discovered that electrical currents actually don't just create electricity, they also create a magnetic field around those electrical currents. Now, if you want to take a quick peek at this video, you can see the experiment and what he did and sort of what the ramifications of that were, because that discovery led another guy by the name of Michael Faraday, and this guy's basically a rock star in the world of electricity and electrochemical science. He discovered that, well, wait a second, if an electrical field can create a magnetic field, could we reverse that? Could we create electricity from simply using a magnet? So could we generate electricity just by using magnetic fields? And the answer was yes. Through his experiments, and again, you can watch the video about his work, and his work was groundbreaking. The guy really came from nothing and basically rocked the scientific world with his experiments. And the guy was one of the most, probably the most inventive experimenters ever in science. He basically determined and discovered that, yeah, you could use a magnetic field or a magnet to actually produce electricity out of essentially thin air. And that was a huge process that he discovered, which was called electromagnetic induction. And that is sort of the basis for pretty much all the electricity we're using today. This guy basically opened the lid. I mean, obviously there were people who created batteries before him, Volta, but he basically found this way to produce electricity that no one had really had envisioned before. And what Faraday had discovered in his experiments was that he used what was called an electromagnet. So what he would do is he would take like a chunk of iron or like a big heavy chunk of metal, and usually iron, and he would wrap that iron up with conductive wire. So wire that could run an electrical current through it. And then what he did is he would run an electrical current through the magnet, and he would actually create this magnet out of it. Is basically what would happen if he ran electricity through it. So because he could create this piece of iron and he could turn it into a magnet by either turning the electricity on or off, that magnet, that electromagnet, would then react with other magnets. Now, you've done this probably at home before. If you've got two fridge magnets or whatever, sometimes when you put those fridge magnets together, they repel each other. And sometimes when you put the fridge magnets together, they stick together. Well, it sort of works very much like what we discussed with positive and negative charged particles in electrical fields. We don't discuss magnetic fields officially in grade 9, but be aware they work in similar ways. Magnetic fields basically have a north and a south pole. And a north pole will be attracted to a south pole will be attracted to a north pole, but a north pole will be repelled from a north pole, and a south pole will be repelled from a south pole on a magnet. So if you've got a magnet, the magnet on one end's got a north pole, the one end's got a south pole. If I have another magnet with a south pole on the bottom, these two magnets are going to repel one another. But if I flip that magnet around and flip it the other way, now the south pole is coming in contact with the north pole below it. They're going to stick together. So when Faraday began experimenting with these electromagnets and actual permanent magnets that were beside them, he could actually make the magnets either repel one another or attract one another. And the way he did that was by switching the direction of the electrical current. If he made the electrical current go one way, the electromagnet and the magnet would repel one another. If he switched the current to the other direction, the electromagnet and the regular magnet would actually attract to one another. So he began to think, could we use this to perhaps create motion? And the answer is yes. The basis for the electromagnet is basically the basis for the electrical motor and how electrical motors work. And again, I would get you to watch this video about electrical motors because it is going to describe it in some good detail. Might be a good video to watch before I give the explanation. That way you've got a little bit of background on how electrical motors work. But what an electrical motor does is it basically uses a permanent magnet, which is my blue magnet on the outside. And on the inside of that magnet, we've got this little squared area here that is indicating my electromagnet that is wrapped around a central shaft known as an armature. And that armature is attached to a circular kind of a ring-like structure that sort of rotates around the armature known as a commutator. The commutator, and it's important to note, the commutator has a split in it. There's a little bit of a break in that ring, and that split is very important. In fact, it's the whole reason why motors are going to do what they do. You need that little split ring to make this happen. So basically what's happening is this. We've got a circuit that's attached to a power source, in this case a battery, and we're running electricity through, and there's essentially two little carbon brushes that are running an electrical current through. As we begin to generate the electricity, this commutator begins to spin. And what happens is, as it hits the brake, when the brake hits the brush, where the carbon is, it's going to cause the electricity that's flowing into this electromagnet that's attached to the circuit and the commutator. It's going to cause the direction of the electricity to change direction. So what would happen is, as this commutator rotates half turn to here, and that little split hits contact with those carbon brushes, the electricity might be flowing in, let's say, this direction. Okay, it's flowing in this direction and coming back that way, which would cause the electricity, or that would cause the electrical current would cause a magnetic field around the electromagnet. At this point, it's going to want to line up because it's going to have a north and a south pole generated by that direction. So let's say right now the north pole's on this side and the south pole's on that side, right? Because I've generated a magnetic field around that electromagnet. Well, right now the S is close to the S, the north is close to the north. Well, that's a problem. This electrical magnet is going to want to spin. And that spinning is going to actually cause the commutator to continue the spinning motion. But what's going to happen is, as it spins halfway, as the south end arranges itself so that it's beside the north end, at that point, the split ring on the commutator is going to make contact on the other carbon brush. And when it does that, it's going to force the current now to switch directions. So the current will now move in this direction, which is going to cause my magnetic field to orient itself back to a north-south direction. So now my north, just when the south end gets lined up with the north end, we play a trick on it. We switch that south end of the magnetic field back to a north end. Well, north repels north, south repels south. So what's going to happen again is it's going to cause this electrical magnet is going to flip again. It's going to flip again because it wants to be back in a position where it's south on this side and north on that side. But by the time it does that, the split ring commutator comes back to the other carbon brush, which is going to cause the electrical field inside the electrical magnet to once again change directions. And when I do that, again, my magnetic poles flip, and so on and so on and so on. So what that does, this constant flipping of the direction of the electrical current inside the electrical magnet, paired with the fact that the electrical magnet wants to flip in orientation to orient itself the right way to the permanent magnet, it's going to cause that thing to continually spin. So we're converting now electrical energy into mechanical energy, which is essentially what a motor does. A motor is designed to take electrical energy and turn it into a rotational energy source that's going to now be attached to an axle. That's going to turn your tires, and your vehicle is going to move, right? So that is how electrical motors work. Hopefully that made some sense. But again, that video I showed earlier, give that one a watch if you haven't. It does explain it actually quite well. Commutator's role in the armature spin, a nice little another analogy here. You can say, it may be difficult to understand for you. Imagine, if you try to imagine a steering wheel. If you put both hands on your wheel to turn, you can't keep turning without letting go. Like if I want to turn my wheel on a car, I have to constantly let go of the steering wheel in order to turn that wheel. That's sort of what's happening here is by we're releasing the current, flipping it to then basically continue the rotation. I don't know if that maybe helps out. That's another analogy that might come in handy. Um, so again, you want that split ring in order to keep that electromagnet inside the permanent magnet moving. Motors can work on two types of current. There are two types of current that we can use in a motor. We can use either DC or AC. You might have heard of AC/DC, the band AC/DC. That is basically, we're dealing with direct current versus alternating current. What's the difference? Well, direct current means the electricity is flowing only one direction in the current. It's only moving one way in the circuit, pardon me. There's only one direction for the electrons to move. This would be the kind of electricity that would be used by small devices with semiconductors, iPads, laptops, iPhones. Most of the small electronic devices in your house are going to be using a DC power source. AC, on the other hand, is an electrical flow that alternates the direction of the electrons in the circuit. It keeps changing them back and forth, and it actually it can rotate them as quickly as up to 60 times a second. So the electrons are constantly moving back and forth and back and forth and back and forth. This is the method of electrical transmission. When we transmit electricity from a power plant into your homes or to a business, we're transmitting that material, we're transmitting that electricity through an alternating current through the transmission lines. The reason for it is it actually reduces the amount of transmission loss. We talked about this earlier in the unit when we talked about maybe the advent of superconductors. By alternating the current, you're actually going to reduce the resistance in the line, which is going to help you get more of the electricity to where it needs to go to homes, to businesses. Now, be aware, once that AC power hits the home, pretty much it's all going to get converted to DC because most of the items in our house are going to use DC power. There are a few larger items in our homes that are going to still need to use AC, so we would convert it back to AC for these products. They have special plugs that will do that. These would be things like your refrigerator, your range, your stove, dishwashers, washer, a dryer. These are going to be using AC power in your house rather than DC. But the question maybe then goes to say, well, why don't we just use DC all the time? Again, I kind of mentioned why we don't use, if we try to use DC with transmission, we'd have all sorts of issues with resistance and loss of signal. Take a watch to this video. This is going to discuss why we actually have AC. There are some times where we need to use AC, obviously, and there are some times when we need to use DC. So there's uses for both, but there's been this ongoing, when do we use AC, when do we use DC? This video hopefully will explain it for you. One last concept today, and that is going to be about transformers. We've talked about motors, which basically convert electrical energy into mechanical energy. Transformers are designed to change the amount of voltage. So if I've got high voltage power lines that are coming into, say, Morinville, I don't want all that voltage entering into a house. So you might notice that even around MCHS or around town, you'll see those big boxes, those big metal boxes around town. They usually have, they have labels on the side that have like pictures of provincial parks. Back in the day when I was a kid, they were the big green boxes, but they look a lot prettier now because they got waterfalls on the sides or the sides of mountains. But there's a couple even like on 101 Ave. If you're walking behind Aspen House, there's a few there as you're walking down toward MPS or to the fire hall. These are your transformer boxes, and these transformers are going to take that high voltage that's coming in from the power lines into Morinville, and we're going to reduce that voltage before it goes into your house. Because if we have that much voltage running into our house, we would have trouble with potentially frying our circuits, frying our breakers, overloading the electrical capacity inside of our homes. So in order to reduce the amount of voltage from one transmission line before it comes into your house, we're going to use something called a transformer. And a transformer simply does that. It either is going to step up or step down voltage. In the case of the transformer boxes here in Morinville, they're all step down transformers. They're taking high voltage into lower voltage that can be used in your home. So what we've got in those transformers is there would be an initial circuit that would be the circuit coming in from the high voltage power lines. It's going to enter the transformer that has a magnet, and we're going to wrap the primary coil or circuit more times around the magnet than the outgoing circuit, which is then going to go the secondary circuit, which is going to go into your home. By wrapping the primary circuit more than the secondary circuit, as we transfer the electrical energy from one side of the transformer magnet to the other, we actually reduce the voltage. That actually is how we reduce the voltage, just by the number of wraps. So the more I want to step it down, the more wraps I want on one side and the fewer wraps I want on the other side. If I wanted to step up my voltage, it would be exactly the opposite. I would have fewer wraps on the primary circuit and more wraps on the secondary circuit, and that would allow me to take a lower voltage and actually increase it to a higher voltage if I wanted to transmit it. And the reason we use high voltages for transmission, again, it's because of resistance. If I can have a higher voltage, there's going to be less transmissional resistance as I move the electrical signal from the power plant that generates the electricity into the homes. So there is a danger with high voltage, but there's a reason we use high voltage in transmission lines. It's because we want to get as much of the electricity from the power plant to the homes and businesses where they need to go. And that is pretty much our conversation about energy transformation. Not that difficult, a couple of new topics. The engine, to me, the motor is probably the most complicated thing that we discussed today. Give that a watch again, listen, read about it in your textbook, go through it in the notes, watch that video that I gave you the link to. That, to me, is probably the toughest concept that we've covered today. Homework based on the topics of 3.1 and 3.2. I'd like you to complete questions 1 to 8 on page 323, and I'd like you to answer questions 1, 3, 4, 5, 6, 8, 9, and 10 on page 331 of the Science in Action 9 textbook. Whew. That's it for today, folks. Join me next time when I discuss efficiency, how we can make energy transformations as efficient as possible. Have a good one.